Hello, everybody, and welcome to episode 76 of the Hyperthesis podcast. I'm Liam.
I'm Feely. And I'm Patrick.
Thanks for joining us today, where we're going to talk about the upcoming eclipse on Monday, April 8th, I believe, right? I got that date right? Yes, so there's a big eclipse happening in parts of North America, and I'm not sure about, I think it's just North America, right? And the three of us are conveniently located, that we're in the totality region, where we get to see 100% eclipse, not just a partial one. Well, Patrick's flying down to where I am to see it, and we're going to meet up and have a little party. But anyway, before we start talking about that, I have an intro topic about the moon, because the eclipse is when the moon comes between the sun and the earth. So I figured I'd have an intro topic about the moon, although it's nothing to do with eclipses. So I found this paper published on February 5th, 2024, in the journal titled Philosophical Transactions of the Royal Society A, Mathematical, Physical, and Engineering Sciences. And the paper was titled Astronomy from the Moon in the Next Decades, From Exoplanets to Cosmology and Visible Light and Beyond. So it was the first of a two-part series of papers, and the scientists from France basically discuss and study how astronomy from the moon could take place and what it might look like and develop, how it will develop in the upcoming years. So the idea is that one day it might be possible to install large telescopes or other kind of instruments, like maybe interferometers, for example. It might be possible to install them on the moon, or even put them on satellites that orbit around the moon. And that's pretty ambitious, but there's some reasons and benefits why you might want to do this instead of just using our regular Earth-based satellites and Earth-based telescopes. So compared to the Earth, kind of the moon has some unique conditions with three immediate advantages that this paper highlights. The first being that it doesn't really have an atmosphere. So this lack of atmosphere means that the entire UV, visible, and infrared spectrums of light are able to kind of reach the telescopes that might be on the moon. There's virtually no kind of molecules floating around in an atmosphere like there is on Earth, and so that therefore the light doesn't get partially blocked, or there's no absorption and emission of light before it hits the telescope. So you can see everything really good on the moon, in principle. And additionally, it avoids kind of atmospheric turbulence and other related effects. So at nighttime, if you look up in the sky and there's no clouds and you see stars twinkling, that's because the atmosphere is it's a fluid, it's moving around. There's turbulence, there's regions of higher density, regions of lower density. It's kind of like how when water goes through a swimming pool, you see all these wavy lines on the bottom. That's caused by these focusing events, because the water has a shape to it. Similar stuff happens in the atmosphere. So without an atmosphere, you don't have to worry about that as well. The second advantage is its low gravity and absence of wind, which I guess is two advantages, but they lump them together in one in this paper. So this could allow for the installation of very large telescopes and other very large instruments, so you don't have to worry about kind of structural stability. I know on Earth there's been some pretty large telescopes that were built, and actually there's that big concrete one built somewhere, and it after many years deteriorated and collapsed due to gravity, so you don't have to worry about that kind of stuff too much.
That's the Arecibo telescope that was in Puerto Rico, and it's very sad that recently collapsed. I believe in 2020 when everything else was going wrong. But yeah, that was an incredible telescope that was quite fundamental to a lot of different discoveries.
So why did it collapse? Was it just was it in the middle of like a rainforest or something? It was kind of in this random spot.
Yeah, just maintenance wasn't kept up with it, and I believe so there was a central structure that was strung up by guide wires, and the guide wire snapped because of lack of maintenance and inspection.
Yeah, so I think that's like the second advantage that they say is that um in principle if there's no gravity then things are less likely well, there's a little gravity but um things are less likely to kind of collapse like that. And additionally, if there's no atmosphere then things aren't going to really oxidize like they would on Earth, for example. Although again, these are all the advantages. There's a lot of disadvantages I'll list in a moment. Um, and finally, the third advantage they talk about is that instruments on the moon could allow for upgrades and long lifetimes. Well, the long lifetimes we mentioned, but so if for satellites that orbit the Earth, it's kind of impossible to send people to them to fix them or to land them on Earth and repair them and upgrade them and send them back up because they have a certain amount of fuel, and when they fall back to the Earth, they kind of burn up and get destroyed. So if you have a telescope or some instrument on the moon, you can send some astronauts there and they can go and fix it and they can, update it. They can download Windows 13 on it, give it that boost it needs.
Well, I think there's an issue of the space junk too, right? Around Earth, there's so many junk around, so much, and the moon doesn't have as much. And we can go a little to the moon too, the orbit of the moon. And I think since you have a less gravitational pull, you can just yoink it into deep space or just way away too, right? Just push it away when it's done, rather than in Earth it might be difficult.
Yeah, you definitely need more fuel to get something out of orbit around Earth if it's already in orbit. Um, yeah, that's also it, right? Like, there's only so much. There's this big problem now about junk around the Earth because we're putting too much stuff in space or stuff orbiting the Earth. So there's this whole problem where we might trap ourselves on the planet by creating too much space junk.
Well, it's in a way we have a lot of space, right? Because if it's, well, if you think of the surface area, because the radius is bigger than the Earth, you have so much surface area. The problem isn't like the area they occupied. The problem is that all of them were orbiting at a very fast speed. So if you don't want to get hit by any like small pieces of stuff, because like when you're on Earth, right, like you're grounded usually, and that's fine. You have junk around that like it doesn't really hit you with very high speed, but on space you might be on a different orbit, and yeah, they might be very fast.
If you have seen the movie Gravity, something like the beginning of Gravity, where some I think a space station is blown up or a satellite is blown up, and then that causes a lot of particulates start moving again quite quickly, especially relative to other things in different orbits, and then they all collide, and it starts a chain reaction pretty much. And the issue isn't really around where the space station is, which the orbits will decay quite quickly. Like they commonly drop things in around the space station. So there was a tool bag a few years ago that was dropped. People were actually tracking that, and that only took a few days to fall out of orbit. It's higher orbits where there's less drag from the atmosphere that this is a problem.
And I think this paper mentions something about the drag of the atmosphere around the moon not being as much of a. It's not as present, so you can.
Well, you said, oh, I mean, there's no atmosphere, so there shouldn't be a
Yeah,
drag from
I think.
atmosphere.
Well, I think the moon probably has like a really, 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 really minuscule atmosphere of some kind. I don't know.
No, I don't think so. There might be some
No.
gas lying around, but I
Well,
think
that's
atmosphere is a very specific
okay.
condition.
Yeah, like there's obviously, some little dust particles floating around the moon, I think, but yeah, it's not like the Earth's atmosphere where it has layers and lots of molecules. Anyway,
Yeah,
so the paper kind of then goes on to describe, all right, like here's some benefits of putting telescopes and things on the moon. What kind of experiments would be worth doing that we can't do on Earth? So they give a really big list of all these scientific goals and potential experiments, and I'm not going to get into all of them that much, but one proposal is to use the Earth's atmosphere like a lens in order to better study stars. So that's an interesting one. So when you could aim your moon telescope at the Earth, and what happens is that as light kind of from behind the Earth passes through its atmosphere, some of it gets focused onto the moon because of refraction. It acts like this big kind of lens, and astronomers do this kind of stuff with planets already, but you could do it with the Earth if you have a telescope on the moon. So what it could do is result in a magnification of up to 50,000 times. You wouldn't be using it to kind of image stars, but you could use it for certain kind of optical observations, like measuring pulsar timings and things like that, apparently. So that's one interesting example. And then there's a whole bunch of other ones ranging from like Earth observations, imaging small bodies in the solar system, like small asteroids, obtaining high angular resolution images of exoplanets and exomoon transit, imaging of stellar glint exooceans, because apparently when you aim your telescopes at planets with water, you get this kind of distinct glinting. It's kind of like, when you look at the water in the ocean, you get these little like reflection spots sometimes, depending on the sun and the water. You could use these moon telescopes to look at kind of gravitational lensing of quasars. And you could even use them. They give this dark matter proposal, although it's like one sentence. Their main focus is on like planets and things like that. But you could also kind of study the Einstein ring distributions of dark matter to look for kind of beyond standard model physics, because I guess if axions exist, which is something we talked about a little bit before, they'll have a particular kind of pattern to them. And I guess on the moon, there's less disturbance from the atmosphere and stuff like that, that you might have the sensitivity you need to see that. So, although having these instrument detectors on the moon has a lot of different benefits, there's a bunch of downsides as well. And so, the big one is lunar dust, which is just formed from meteorite impacts and human activity. So, the moon's a pretty dusty place. Anytime something moves, a lot of dust goes everywhere, and dust on your instruments is very bad. Another problem is that if your instruments are there over long time scales, meteoroids could hit them and damage them. The moon gets hit with a lot of meteoroids over long time scales. Lunar seismology is something that could cause problems for if you had an interferometer, for example, or really sensitive telescopes, they could unalign.
I mean, it's the double-edged sword, right? Like
Yeah.
for the atmosphere, the lack of it is like, well, there's nothing to protect the moon from getting bombarded. Like we can see any in the pictures or the images of the moon. It's like, well, it's filled with holes, man.
Exactly. So you'd be kind of, I mean, it'd be a risk putting a telescope on the moon, because eventually you have to assume it's going to get dinked by something. And then a couple more problems are just the stability of the ground that the instruments are being built on, depending how big they are. Like if you build one of these big massive radio telescopes, right? Like we've never really built things on the moon, so we'd have to learn how to do that. How stable is the ground it's being built on? Another problem is the day-night cycle. The difference in temperature between the day and night on the moon is about 350 Kelvin, which is a lot. So you need instruments that could withstand that. And then there's some other factors like cost and accessibility. So, sending up all the materials to build the telescope on the moon is probably pretty expensive. Sending up astronauts will take a while. We'd have to if they're going to build the telescope, they have to live on the moon for quite a while to build it, presumably, which we haven't mastered yet. So there's all these different factors that need to be overcome, and there's some benefits to it, but who knows? Maybe one day we'll get there.
So just on this topic, there is an excellent video done by the Real Engineering YouTube channel, and this outlines how we can actually build a telescope on the moon. So there are a few different criteria, such as making sure that the crater they're working in, because they'll be working craters specifically, it has to be quite circular with a very well-defined ridge all along it, so no interruptions, and again, quite circular. It has to be in the right place, as you discussed, Liam. And then they also will, for this plan, which is done up by NASA, they want to send a probe, which will essentially fire anchors out into the sides of the crater, kind of over that little hump that leads into the crater, and then suspend a telescope from there. So it's a completely automated process, no humans needed or involved. And I would really recommend checking out that video. It goes quite in depth with the engineering and feasibility of a project like this, and the animations are also really good for visualizing this. But there are a lot of complications with it and a lot of different considerations, such as if you have a lander that's firing rockets at the moon's surface, you're going to kick up a lot of dust. So how long do you wait? How do you make sure that signal is able to get to Earth when you can't maybe see the side of the moon that you're actually operating on? There are a lot of complications that need to be considered, but it is something that NASA has planned.
I think in this paper, actually, they talk about that kind of scenario a little bit. This paper's figure 9. They have a photo of this telescope being suspended in a crater with cables, and they call it a hypertelescope. Maybe that's a particular type of telescope just being suspended by cables, but it looks like they're kind of using the actual crater itself to like help focus things, which is kind of neat. So it's a minimal assembly required situation, which is nice.
Yeah. And this one actually has a name. It's called the Lunar Crater Radio Telescope, or the LCRT, which has a Wikipedia page and a lot of other information about it.
Cool. All right. Well, that's some up and coming science on using the moon as like an observation post. However, that's not the main topic we're here to talk about today. Today we're here to talk about a very rare occurrence, a solar eclipse, which we'll all be seeing. Well, the three of us will at least. So Patrick, you've prepared some stuff on that, I believe.
I have. So to begin with, solar eclipses themselves aren't that rare. Total solar eclipses are a lot harder to come by.
Okay.
But we'll get more into that a little bit later. So as Liam mentioned at the beginning of this episode, we have an upcoming total solar eclipse happening in North America. It starts kind of in the south for us, Pacific, kind of off the coast of Mexico, and then tracks through Mexico, the United States, and then up through Canada, starting in the Toronto area, and then moving all the way into Newfoundland and Labrador. So this is very exciting because over 30 million people alone live in the eclipse path where totality will happen. It includes big cities like, I believe, San Antonio, Texas, also Montreal, not quite Toronto, but close enough to Toronto that I think they considered the GTA in that number. So there's millions of people that can view it, and then millions more, myself included, that will be visiting to see what the eclipse is all about.
I was going to say Toronto's something silly like 98 or 99% totality, I think, because I'm in Hamilton with 100%, and I'm like a stone's throw from Toronto.
Yeah, can you even tell though with 99%, like 98? Probably, actually.
Yeah, and that's the thing is, what actually constitutes a total solar eclipse, and why is everyone flocking to this small path? I saw a number, I think in the CBC article not long ago, that Niagara Falls, which is pretty much right in the center of the path, along with around Buffalo, New York, it's expecting 1 million visitors for just the day, which is insane. But there's a reason why people go to see these eclipses. So
totality is like 3 minutes, right? It's not just a day. It's like, well, we're gonna fly here, do stuff for the 3 minutes of this wonderful thing.
Yeah, so where I'm at in Hamilton, I think it's like the eclipse starts at 2, totalities for a few minutes somewhere around 3, and then it ends around 4. So it's like a 2-hour event, but the big, the moment everyone's waiting for is only a few minutes, like you said.
Yeah, and that's the thing, it's a few moments. Like, I'm flying all the way to Ontario just for, I think it's something like 98 seconds in Hamilton, in which we'll actually have a total solar eclipse. And that's just, I mean, that's not a lot of time, but pretty much every account that you hear of a solar eclipse, which we might be getting into later, it says it's a phenomenal experience.
Yeah, and it's you're always at the mercy of the weather too, right? Because like it could be like just a rainy, cloudy day, and we'll still notice it. It'll get dark out, which is kind of cool. But I have my eclipse glasses. I want to get photos of the actual totality thing because it's this really cool black dot in the sky surrounded by this kind of bright ring. I want to see one before I die. So I hope to God that we get no clouds, or even if it's not rainy, there could be just like one evil cloud that just goes in front of it during that 90 seconds, and it's like, no.
Fingers crossed not. I bought a solar filter for my camera just for the eclipse, and yeah.
I was gonna ask if you brought your nice camera, if you're gonna, well, not brought, but if you're gonna bring it.
Oh heck yeah.
Oh, good.
Well, I think even though if it's gonna get cloudy, I got this software because I'm marking astronomy class right now, and it's called a Starry Night. So you can like kind of simulate everything, and it's like, I mean, one part of the assignment is to simulate the eclipse. Like not really simulate. It's like you can go to exact date and time and location of any place and look up to the sky, and they track all the motion of the celestial bodies, and you can see the eclipse is really cool. And yeah, it's not ray tracing graphics, but it was all right.
So we're talking about this. We're excited to see it, but why exactly is an eclipse so special? Because eclipses themselves are actually a common phenomena. They happen every year, sometimes multiple times a year, but we make a big deal out of these total solar eclipses because they're a very specific type of eclipse. But before we get into exactly what happens there, it's important to go over the other types of eclipses. So we mentioned Toronto, it wouldn't get that full eclipse. It will get what's known as a partial solar eclipse. Now, these are actually quite common. So they can happen multiple times a year. I was just looking yesterday at some upcoming eclipses in Canada, and in 2029, I think we get 2 partial solar eclipses. But that's where the moon is not able to fully cover the sun. So for the total solar eclipse, the moon is able to completely cover the sun and essentially blots it out of the sky. And since these are very large celestial bodies, it's able to do that, whereas just kind of putting your hand up in front of you, between you and the sun, that's technically an eclipse of your hand, but it doesn't have quite the same effect as the moon casting a shadow on the earth. Now, there's also another type of eclipse known as an annular eclipse. Now, this is something that happens, like the name would suggest, every year, but this is also a little bit different because of the placement of the moon and the sun isn't quite enough to actually cover the sun fully. So it's still cool to experience. There's a lot of dimming that happens, but it's not the same as this total solar eclipse.
I think we experienced one of those at our undergrad university. There was one day there was like a partial eclipse, and we had the telescope out, and I don't know if you were there. I thought you were, but
that was for the total solar eclipse that was happening in 2017. So for us, it was a partial.
Yeah,
eclipse.
We weren't in the totality region.
Yeah.
So the sun got like half covered, and you could see it in the telescope, which was cool. And it was kind of cool because even though you couldn't really tell I mean, you're not supposed to look at the sun. Same for an eclipse. Don't look at the eclipse. You're supposed to have these special kind of like welder glasses, or I don't know, so you don't blind yourself. But it was kind of cool because you couldn't really tell that from where we were, nothing really dimmed that much, but the temperature dropped a bunch. It was kind of cool to look at the sun through the telescope with a solar filter, see that about half of it got covered by the moon's shadow, and then the temperature outside, it was in the middle of summer, it was like 25 degrees or something, and then the temperature dropped like 5 or 7 degrees. So I thought that was pretty cool.
Yeah. So that was, again, a partial solar eclipse. So you don't get this full obscuration of the sun. It's just a partial. The moon's kind of in the way. Now, to explain especially why these partial solar eclipses happen and why an eclipse can happen in the first place, it's important to discuss the size of the sun and the moon and their distance from the Earth. Before then, though, I do just want to mention lunar eclipses also exist. They are decently common where the Earth gets between the sun and the moon. So the Earth casts a shadow on the moon. It can cause a very red-looking moon. Super cool. But that's not about this. This is about solar eclipses. And the fact that solar eclipses happen is kind of a nice alignment of celestial bodies. So the moon is about 250,000 kilometers away from the Earth on average. And then the sun is about 150 million kilometers from the Earth. Now, doing just a little bit of math, the moon is about 400 times closer to us than the sun. So if you were to just measure distance between us and the moon, take that by times 400 and you have the distance to the sun, or about 1 AU, or astronomical unit. Now, the nice thing is that diameter-wise, the moon is about 400 times smaller diameter than the sun. Now, the fact that it's about 400 times closer and 400 times smaller means that when you look into the sky, the moon and the sun are about the same size. So a really cool trick you can do is you can take something small, like say a dime or a 10-cent piece or even a penny, if you still have them in your country, and you can hold it up and look at it and compare it to, say, the moon and the sun. Again, try not to look directly at the sun, but you can see that the moon and the sun will be about the same size when comparing it to the penny. This works really nicely because since they're the same size, that gives the moon the ability to block out the sun occasionally. Now, you might be asking, okay, so why doesn't the moon always cause an eclipse? Because every time there's a new moon, that's where the side of the moon that's illuminated is directly facing the sun, and then the moon is dark to us. We can't actually really see it because it happens during the day. But when a new moon happens, the moon should be between us and the sun, but the moon's orbit is actually tilted relative to the orbit of the Earth and the sun. So if the Earth and the sun, that orbit makes a nice little plane, a little ellipse, and then you look at the orbit of the moon, it's tilted by a few degrees. So essentially, these celestial bodies have to line in such a way that the orbit of the moon is tilted in the right way, that it's able, when it's in its new moon phase, it's able to pass between the Earth and the sun exactly so that everything lines up in a straight line. So for this, since the moon takes about 28 days to orbit, and then the Earth takes 365 days to orbit the sun, there's essentially, it's a property of math. So when will the moon actually line up, and where will the Earth be during that time? It will always be during a new moon, but this is why we don't have total solar eclipses every time there is a new moon. It only happens once every few years. And for total solar eclipses, they happen even fewer because, again, we kind of have an eclipse every year, but it's not always this total solar eclipse because it also depends on where the Earth is in orbit. So the Earth has an eccentric orbit around the sun, meaning that it's closer during part of the year and further away from the sun during another part. And when it's closer to the sun during the, I believe it's the North American summer, so it's closer, it's North American winter, that it's closer to the sun. So when the moon is orbiting, it's actually just ever so slightly smaller than the sun in the sky, which means that even if it completely blocks the sun, if it's perfectly in the path, there's still not a total solar eclipse. You definitely get a lot of dimming, but there's still light from the sun reaching around the moon. Now, in the North American summer, when the Earth is furthest away from the sun, the moon is now slightly bigger than the sun in the sky, so it causes this total solar eclipse. So in North American summer, you are more likely to actually see a total solar eclipse than a a Northern Hemisphere summer. You're able to see a total solar eclipse more than you are likely to see a total solar eclipse in the Southern Hemisphere summer. It's just the way that things align. And when the moon passes in front of the sun, but there's still some sun shining along the outside, that's what's known as the annular eclipse. So it has to do with sizing and positioning and just the alignment of these celestial bodies, which we can well predict. So we know when the next solar eclipses are for a very long time, but it just takes the perfect alignment for us to get what's happening this year in a couple days, which is the total solar eclipse.
And what makes it more rare too is that the total solar eclipse doesn't appear the same place often. To give some idea, I think in where I am in Kingston, last time it was almost 700 years ago that it happened. So, and the next time I think they calculate to be 2399. So we all be gone in the ground or as ashes. So this might be a one in a lifetime experience unless you want to travel just to see the eclipse, right? Sometimes you have to even travel internationally.
It's interesting because in Hamilton, the next one is in 2144, I think, which relatively isn't that long, but I think I'll be dead by then. Unless technology really keeps me going. But
We'll be seeing the eclipse in the Matrix by then.
oh yeah, exactly.
But yeah, so these are super rare, and it's interesting. There is a great video done by Minute Earth that showed essentially why the northern hemisphere gets more total eclipses. And I'm just looking for the number now, but essentially because of the fact that the Earth kind of wobbles in its orbit, it means that slowly but surely the moon or the northern hemisphere summer will happen on the opposite side of the sun eventually, meaning that essentially the southern hemisphere will start to get more solar eclipses. Now, this will take tens of thousands of years. And as of right now, in the northern hemisphere, for any single place on Earth, the average for a solar eclipse to happen, or the space between a solar eclipse, total solar eclipse specifically, is 330 years. Whereas in the southern hemisphere, that same time between two total solar eclipses is 550 years. So there is a big difference. And there are a couple places, of course, this is on average, but there are a couple places that have to wait a long time. Like I think there's a place in New Zealand that wouldn't get a total solar eclipse. Their last one was in 69, and the year 69, Common Era. Very nice. And then their next one wouldn't be until 2431. So quite a lot of space, whereas a place in, I think it's not Idaho, but Indianapolis or somewhere in the kind of Midwestern United States, they had two eclipses within 7 years, and that was the 2017 and the 2024 eclipse. So for these solar eclipses, the orbits are important. It's also important to be in the right place on Earth. And something that's really cool is that we will not have solar eclipses forever, or total solar eclipses forever, because the moon is slowly getting further and further away from the Earth over time. So it's further away than it was when the dinosaurs were there. So the dinosaurs most likely had pretty much solar eclipses anytime there was an annular eclipse. It would have been a total solar eclipse. But because the sun has moved, or the moon has moved away from the Earth, these are becoming rarer and rarer, and at some point we'll just stop getting total solar eclipses. Now, this will not be in our lifetimes in any way whatsoever, but it's just kind of something cool to know that we're in a good time for solar eclipses.
How much does it move every year on average? Not very much. It's like in the centimeter range or something.
It's just under 4 centimeters per year on average.
Mm-hmm.
So it's not a lot, but over millions and millions of years, it does make quite the difference. So there are some interesting things, especially if you're watching the eclipse, to watch out for. So there's a lot of different phenomena that happen during an eclipse, and also a lot of different measurements that can be made during an eclipse. So as the eclipse approaches and the moon starts to block the sun more and more and more, of course, as Liam said earlier, in the last total solar eclipse in North America, the 2017 one, there was definitely a drop in temperature. Now, this drop in temperature can also lead to the formation of clouds, which quickly dissipate, but there's essentially cooling of the atmosphere because there's less radiation coming from the sun that's hitting the ground and then being radiated outwards. So you actually get kind of these clouds forming, which is a super cool phenomena, something to look out for. Also, as the sun begins to cover more and more of the disk, or the moon begins to cover more and more of the disk of the sun, you also start seeing stranger shadows. So a really cool way, if you don't have eclipse glasses, to observe the eclipse is with what's known as a pinhole projector. So if you take just a sheet of paper, poke a very small hole in it, and then have another sheet of paper kind of acting as a screen, you can see the light coming from the sun that's projected onto that piece of paper through the pinhole, and you can actually observe the moon as it traverses across the face of the sun.
You can kind of see it in if you're somewhere that has leaves on their trees right now. The leaves might have little holes in them and stuff, and you can kind of see in their shadows that effect as well. I'm pretty sure. And I forget, there's a good video on YouTube. I forget which one, but it explains like how this works. How is it that this small little pinhole is projecting the moon's shadow when the moon and sun are so far away? And I completely forget how it works, but I don't know if anyone here knows.
Well, it's just I think it's one of the main principle of the early camera too. It's called a pinhole camera, right? And it's basically just a little hole, parallel light come in, and then just get projected to a screen. I think it's pretty straightforward.
Mm-hmm. The sun's interesting because it doesn't produce parallel light, and often you can't like there's many like applications or things where you can't assume it's parallel, but then there's a bunch that you can.
Oh, this is not exactly parallel light, but
Pretty
let's
parallel.
say the light. No. I mean, like, okay, it's parallel in that sense, but the lights that coming from the top would come in at an angle, right, into that hole, and the light from the bottom also come from the bottom on the angle, and that's kind of go through the same hole and get projected. So it cuts out all these stuff that you don't want that from the other angles.
So with light as well, you'll actually start to see some effects of the light as the face of the sun gets towards total coverage. So in kind of the 80 to 90+% coverage of the sun by the moon, you'll also see that shadows start to look different. So because of the fact that essentially most of the sun is covered, if you have, say, something 90 degrees, so 90-degree angle, so if you have like an angle ruler device and you hold it up directly to the sun and look at the shadow, you'll see that one dimension of the shadow is sharp, while the other one is actually blurry. It's kind of fuzzy, and these are known as fuzzy shadows, and it has to do with the position of the sun and the moon. So as the moon comes closer and closer to covering the sun, essentially that kind of crescent of the sun that's still visible, if you went across the length of the crescent, that line will, any object that's perpendicular to that will appear to have sharp shadows, whereas anything that is kind of parallel with the line across that crescent will be fuzzy. So this is a phenomenon that you can watch out for.
I think I add another thing onto the pinhole thing because it's like a matter of aperture. I think last episode we kind of talked a little bit about vision, right? And one thing you could do is when you squint your eyes, you can kind of tell that things get a little sharper, right? When we try to see, well, especially as we all wear specs, so and when we don't have them, it's kind of everything's kind of blurry. But if you squint a little bit, things get a little bit sharper but darker, right? Imagine the pinholes, kind of the same principle. You lower the the lights from the angles you don't want by squinting a little bit. I think that's pretty common thing when people do when they can't see well.
So just another optical effect while we're speaking about them is if you look at the shadow of other objects as the moon gets very, very close to covering the surface of the sun, you get what are known as shadow bands, which race across the ground. So these shadow bands are kind of alternating bright and dark regions at the edge of the darkest part of the moon's shadow, and they're typically spaced inches apart. So they're most easily seen on something that's a white background, but they kind of look like snakes that are like wiggling on the ground. And again, if you're in a place with leaves, you can see them as they cast shadows, but there's a lot of interesting effects as like you're right before totality. A couple other things to mention are there's sometimes an eclipse breeze, especially if you're to the east of a hilly area, because the hills will cool down. This will cause the air to cool down, and then it will flow down the hill towards you. So before the eclipse actually hits where you are, you might feel a stronger breeze. And then as the sky goes black and the moon covers the sun in totality, animals have no idea what's happening. And you might hear strange behaviors. One common one is that birds will go quiet and crickets will start because they think it's nighttime when it's dark. So there's a lot of confusion with animal behavior that's fun to listen to, especially if you're away from a city. Now, the final effect that you should definitely look out for is known as the penny effect. And what this is that, again, as you're nearing totality and more of the sun is getting covered, your eyes do something funny. And that's essentially your eyes see things as being less bright in terms of color. So bring along some bright colored pieces of paper or wear like a very bright green or red shirt, and the actual cones in your eyes will start to be affected by the difference in sun coverage or the sunlight that's reaching you, and saturation will be lost. So it's almost like you're moving a saturation filter in Photoshop or an editing software, but it's happening in real time in the real world. So these are some very, very cool things to look out for. So make sure you're wearing bright colors, bring something that has perpendicular right angles, and then also just keep an eye out for different behaviors and shadows and other effects of the eclipse. And one more thing, just with that, is there is an excellent app made by a solar eclipse scientist who is very passionate about it. So it's on Android. I don't know if it's on Apple, but it's the solar eclipse timer, where you enter your location. It's able to calculate exactly when the eclipse will happen and the timing of everything, and it will actually tell you to look out for these different things. So it's narrated by that scientist, and it's really well done. Super excited to use it. And so he'll tell you, okay, take your glasses off, look up. Okay, put your glasses back on for safety. Now look up. So it's a very good app. It's tied to your location, so it should be pretty accurate. Would highly recommend it.
I think my last comment on the eclipse is that, if it happens in your area or happened to be in the past, just look it up. If it is, go get the glasses, go watch it. It's rare. And also for the resources, just look up any kind of institution, especially academic institution in your area. Usually universities have them, or maybe your local astronomy museum or any type of outreach in science, they usually have them.
Yeah, McMaster's physics department is hosting a whole event where they booked out the football stadium, and they're bringing like food trucks and stuff, so the whole university can watch it. I mean, that's not what I'm going to do because I didn't realize that until too late and I didn't get tickets in time. But they have this whole outreach thing, and the university had, I think, 600,000 pairs of um, Eclipse glasses that they distributed to libraries and the public and stuff. So, and you can even, like, a lot of people I know, they ordered Eclipse glasses on Amazon. I mean, it's probably too late now, but you can try and find someone who has some, and maybe you can share. One eye per. You can look in one lens, and someone can look in the other lens.
Another thing is that there are other institutions, even if you aren't in the path of totality, that might be doing observations. So I know out in Alberta, the university is doing partial eclipse observations using their telescopes and solar filters. And then there's also a couple other kind of science-related places that have open observations where enthusiasts bring out their telescopes and you can watch it all. So go check out what's happening in your area. Even if you can't make it to the eclipse zone of totality, try and watch it anyways, because it's cool to see something so pivotal to life on Earth being blotted out by the moon.
Well, thank you very much, Patrick, for telling us about the eclipse, and I'm very excited for you to come here, so we can watch it together, very romantically. So that's exciting. It's exciting. Yeah, I'm again praying that the weather cooperates, but at the very least, we'll get to experience a little bit of darkness during the day, which is always interesting.
Absolutely.
All right. So today we're gonna end our story, or not our story. We're gonna end our episode with a story, which Feely has meticulously prepared for us through great effort. But first, Patrick's gonna tell you how to reach us.
Okay, so if you are interested in learning more about the eclipse or want to tell us about your experience with the eclipse or where you'll be for the eclipse if you're in North America, then you can reach us over multiple different ways. We have an email. We are hyperthesispodcast@gmail.com. You can find us there. You can send us emails, comments, feedback, or if you would like to be a guest on our show, if you are an eclipse expert or you study eclipse or things about the sun's corona or relativity, we would love to have you on.
Or if you happen to get any good photos of it, either like, with a camera or with a telescope, send them to us and we can have a look at them and post them on our Instagram. That would be awesome.
Yes. And we will definitely credit you, and we'll
credit you for sure.
We'll be also, I'll be bringing a nice camera with a solar filter, but this is my first time photographing the sun, so if you have any tips, feel free to let me know. If you would like to reach us but don't want to use email, we are also on Instagram. We are Hyperthesis Podcast at the Hyperthesis. So you can check out images on Instagram. If you do send us an eclipse image, we will post it on our Instagram and make sure that you are credited as due. We also post updates when we will be posting episodes, and as well as some other things such as memes, which we haven't done in a while, but that's okay. We'll get there eventually. We're all busy right now. If you are listening to us, congratulations, you found us. Hopefully you found us before the eclipse. But if you did not, well, maybe you can use this episode to prepare for the next eclipse that you'll be watching. And if so, you can share us. We are on Apple Podcast. Google Podcast is not dead in Canada yet, but it is dead in the United States. So YouTube Music, just gonna let that sigh ring out. We are on Audible, and we are based out of Spotify, but we are on pretty much whatever podcasting service you may use. We are also on YouTube. You can check out our excellently rendered videos, and well, they look good. And the cool thing is that if you watch the videos during the eclipse when that saturation goes down, you wouldn't be able to tell with our latest season that the saturation has gone down because they are pretty grayscale, it looks great. So you can give us a like or subscribe on YouTube. Make sure to share us, give us a rating, comments. We love feedback. And if you have suggestions for future topics or would like to be a guest on the show, you can reach out to us through many different means.
Thank you very much, Patrick. All right, so our story today, Feely's gonna take it away and tell you what it's about.
All right. So today it's a story that I've heard. I think when I was very young, there was like a little cartoon, like a comic that teach people about math. And one of the things is that, well, not just math, it's science and in general. And one of the things that is like a little kid time travel into ancient Greece, and there was this battle that happened that got stopped because people look at the sky as like, well, the sun is gone. Oops. They're just like, oh, let's not fight. Um, but I think the detail is a little more complicated. So this is called the Battle of the Eclipse or the Battle of Hales. So it was fought in the early 6th century BC. But since we all, we know start science, we can calculate exactly when the eclipse happened. So it's on 20th of May, 585 BC. There's some dispute on if it's the things actually happened, but well, it's supposed to be in Anatolia or present-day Turkey between the Medes and the Lydians. And according to the ancient Greek historian Herodotus, he recorded a lot. So the battle was interrupted by day turning into night. So basically, solar eclipse. And the result was a draw, so that led both of the parties negotiating a peace treaty, ending this not that long, but only 6 years war. So Herodotus writes that in the 6th year of war, the Lydians and the Medes, they're engaged in this kind of long, prolonged battles. Nobody's winning when suddenly day turned into night, leading to both parties halting the fight because, is people didn't know about eclipse then. And when the sky turned dark, this must be very scary. That like, well, maybe the war they're doing is wrong. So Herodotus also mentions that the loss of daylight was predicted by Thales of Miletus, but however, there's dispute on that too. That they didn't have the technology or the calculation to do it at the time, and it's like exactly that's where it's gonna happen. So he wrote in the history as afterwards, on the refusal of the Alberta to give up his suppliants when Cyaxares sent to demand them of him, war broke out between the Lydians and the Medes, and continued for 5 years with various success. In the course of it, the Medes gained many victories over the Lydians, and the Lydians also gained many victories over the Medes. Among their other battles, there was one night engagement, as, however, the balance had not inclined in favor of either nation. Another combat took place in the 6th year, in the course of which, just as the battle was growing warm, day was on a sudden changed into night. This event had been foretold by Thales the Milesian, who forewarned the Ionians of it, fixing for it the very year in which it actually took place. The Medes and Lydians, when they observed the change, ceased fighting and were alike anxious to have terms of peace agreed on. And as part of the terms of the peace agreement, Aeetes' daughter, Aryanis, was married to Cyaxares' son, Astyges, and the Halys River, in the present-day Kerstimak River, was declared to be the border of the two warring nations. And that's the story for today.
Thank you very much, Feely, for that very interesting story. I think it's kind of cool that you can actually use they use the solar eclipse to kind of date when this battle happened, because in the history they said, an eclipse happened during this battle, and we can use the math and physics we know to calculate exactly when this eclipse happened back then. So it's an interesting example of using astronomy in history. But yeah, so thanks everyone for joining us. That was episode 76, and we hope that you got to hear this before the eclipse. on Monday, April 8th. Different times depending where you are. But thanks for joining us. Bye, everyone.
Bye, everyone.
I'll see you next time. Take care.